Welcome to Lesson 20 of GMAT Math Basics. Today, let's discuss problems that involve more than one equation, which we usually call systems of equations. Now that you understand how to simplify equations from our previous lesson, let's build on that skill set and discuss a slightly more complex situation. It's very, very common on the GMAT to have more than one equation in a problem. This is also a natural extension of the way that the exam likes to take simple concepts and make them complicated for us to deal with. So it's very worth understanding how to handle multiple equations at the same time because it's very likely you'll see quite a few problems that involve more than one equation. Before we dive in, here's a quick quiz covering what we'll discuss. There's a quiz like this at the start of every episode in this series if you want to test your knowledge over time by simply flipping through the first few moments of each of these episodes on a regular basis. And I strongly recommend that if you find it helpful. Question one that we'll answer today. Number one, what is a system of equations? Question two, how do we solve systems of equations? Question three, how do we perform the substitution method well on the GMAT? Next, how do we perform the elimination method well on the GMAT? Question five, how and when do we use the graphical approach? Here we go. First, let's define what a system of equations is. A system of equations means two or more equations that involve the same set of variables. For example, consider the equations x plus y equals 10 and x minus y equals 6. Here we've got two equations, and they both involve the variables x and y. This is what we mean when we say two or more equations that involve the same set of variables. It's worth noting, though, that each variable does not necessarily have to be involved in each equation in order for it to be considered a system. I just gave you a sort of straightforward, simple example there. An example of maybe a more complicated situation would be maybe three equations, such as z plus p equals 7, z minus m equals 4, and p plus m equals 20. Even though each variable does not appear in each equation, this is still technically a system because the overall set of three equations deals with the overall set of three variables, z, p, and m. So that's what we mean when we say a quote-unquote system of equations, two or more equations that involve the same set of variables. Now, it's not enough to just recognize that you're dealing with a system of equations on the exam. You'll also frequently, maybe always, be asked to solve that system of equations. So how do we solve a system of equations? There are actually a ton of ways to solve these systems, but GMAT problems really only focus on two main approaches and then very, very rarely a third approach. So that's what we're going to discuss in today's lesson, just those three ways. And we're going to spend most of our time on the two main ways, hopefully for obvious reasons. I'm going to touch on all three briefly here and introduce them to you, and then we'll dive into each approach one by one to make sure that you understand them all well. The two most common techniques on the GMAT are substitution and elimination. The third, much less common approach is called the graphical approach. Substitution is usually the most familiar of these approaches to people and likely the approach that you have the most experience with from your past math instruction. Substitution involves isolating one of the variables, then plugging the equivalent value into the other equation or equations. I will break that down in depth, don't worry, but just to repeat it, substitution involves isolating one of the variables, then plugging the equivalent value of that variable into the other equation or equations in the system. What that means is you may solve for x in one equation and find that x equals 10 minus y, for example. Let's say something like that. And then you would replace x in the other equation with 10 minus y because x and 10 minus y are equivalent values. We'll talk about the mechanics of this approach in depth momentarily. For now, it's worth understanding that the goal of this approach is to reduce the number of variables and the number of equations until you can obtain a numerical value for one of the variables. That's the first goal. Once you have that numerical value for one of the variables, you can use that to solve for the other variable or variables in the system. Again, the goal of this approach is to reduce the number of variables and equations until you can obtain a numerical value for one of the variables. Once you have that numerical value, you can use that to solve for the other variable or variables. Once you have all the values of all the variables, you've quote unquote solved that system of equations. You've found the numerical values that work in all of the equations involved. Substitution is a very, very helpful way to do this. Again, more on substitution in a moment. The other primary method is called elimination. Elimination, which is sometimes called combination or adding and subtracting equations, involves, as you might guess, adding or subtracting equations in order to accomplish actually the same objective as substitution. We want to eliminate variables and equations until we can obtain a numerical value for one of the variables. Then we use that numerical value to solve for the other unknowns. So it's another way of accomplishing the same objective. In some situations, you may favor substitution. In other situations, elimination might work better. And we'll talk about how to make those kinds of judgments in a little bit. The final approach is extremely rare, but is technically called the graphical approach. This uses a graph of two or more equations to find a point where the graphs intersect. At this point, each of the variables will have the same value in each of the equations. Again, this approach is super rare, but it's useful conceptually when it comes to understanding systems of equations. And it is also technically possible that you will see a problem involving the concept. So for the sake of completion, we'll discuss it very, very, very briefly near the end of the lesson. Let's dive deep into substitution, though, since that's something you're going to be using probably quite a bit on test day. So how do we perform the substitution method well on the GMAT? Just for clarity, we're going to talk about how to do substitution on the GMAT exam. So this is not a general math course, and a general math course, honestly, is not what you need at this stage of your MBA journey. We want to stay focused only on what's relevant to the test. And if you want a PhD in math later, then there's quite a bit more to discuss about the substitution method, but we're not going to get into that. Like I mentioned just a moment ago, substitution starts with isolating one of the variables. Let's talk about exactly what I mean by that. Let's use the example we began the lesson with. X plus y equals 10 and x minus y equals 6. I'll probably say this a couple more times, and I've said this in the past, but if you're on the pure audio feed and you're on the go and you don't have a way to write this out, don't worry so much about the actual numbers and variables that I'm going to be talking through. Focus more on the concepts behind them, and I'll do my best to emphasize that. Now, first things first, when it comes to substitution, is that it's valuable to know that we can begin by isolating either variable. So with x plus y equals 10 and x minus y equals 6, we could start by isolating x, or we could start by isolating y. I'm actually going to take you through both ways just for learning purposes, even though you would virtually never do both on an actual test. But I think it'll help you understand and internalize the concept, which is really the goal of our lesson. So let's start with isolating x, and then we'll do the same with y later so you can see what I mean. Isolating x involves just using the rules of equations that we discussed in our previous lesson. Let's isolate x in the equation x minus y equals 6. To isolate x, which means to just get it by itself on one side of the equation, all we have to do is add y to both sides. If we take x minus y equals 6 and we add y to both sides, we'll end up with x by itself on the left side of the equal sign and 6 plus y on the right side. If you don't understand how that's happening, then please go back to the previous lesson and I'll walk you through all the basics you need there from the ground up. Let's just pause and think about what this means, though, for a second. If we had done that operation and isolated x, this means that x and 6 plus y have exactly the same value. Now, that might be a little bit redundant for some of you. You're like, yeah, it's an equation, Isaac. I get it. But I really want to keep us grounded in the core absolute basics here, because while some of you might be very advanced at this stage in your journey, others of you might be relearning this or maybe even learning this well for the first time if you didn't have great math instruction from a young age. And I really want to be sensitive to that because all of you have equal or more value to bring to the business world than any of the rest of us. And I think it's absurd that a test like this would stand in your way of making that contribution. So let's get down to the hardcore basics here. So we just added y to both sides of x minus y equals 6, and we got x equals 6 plus y. That means x and 6 plus y have exactly the same value, which means that they're interchangeable. So that means we can replace x with 6 plus y anywhere else in the system of equations. Let's think about a real-world example of this concept for a moment. Would you hesitate to swap 5 $1 bills that you had for a $5 bill from your friend if she asked you to? You probably wouldn't even think twice about it because 5 $1 bills has exactly the same values as a $5 bill. Excuse me. 5 $1 bills has exactly the same value as a $5 bill. This is similar to what we're going to do when we use the substitution method. We know that x and 6 plus y have the same value, so what we're going to do is replace x with 6 plus y in our other equation. Recall that the other equation in this situation is x plus y equals 10. If we replace x with 6 plus y, then we'll wind up with 6 plus y equals 10. So the x in x plus y equals 10 gets replaced with 6 plus y because they have the same value. Now all we have to do is use some of the rules of algebra we talked about last time and combine some like terms. So we can add y plus y to get 2y on the left, and technically on the left now we would have 6 plus 2y. And then we can subtract 6 from both sides of 6 plus 2y equals 10. We can subtract 6 from both sides of that to get 2y equals 4. All that we have to do there is divide both sides of the equation by 2 to isolate y, meaning get it by itself on one side of the equation, and we would get y equals 2. This is exactly what I was describing earlier. We isolated x, we replaced it in the other equation with its equivalent value, and that allowed us to solve for the numerical value of y. Now all we have to do is use that numerical value of y to find the numerical value of x. Now, we can use either of the original equations to do this. I'm going to choose x plus y equals 10 first, but we equally could have done it with x minus y equals 6, but both ways work. Let's start with x plus y equals 10, though. So because we know y is 2, we can substitute 2 for y, and we would get x plus 2 equals 10. If we subtract 2 from both sides of the equation, we would then wind up with x equals 8. And now we know the solution to this system of equations. X is 8 and y is 2. 8 plus 2 equals 10, and 8 minus 2 equals 6. We've solved that system of equations. Now, we could have also plugged in y equals 2 into x minus y equals 6. If we did that, it would become x minus 2 equals 6. And all we would need to do is add 2 to both sides, and we would have x equals 8 again. So feel free to choose the path that's easiest for you in the moment, since you'll get the same result either way. And I like to make that point because there's many times on the GMAT where one equation might be easier to plug into than another, or one variable might be easier to isolate first than another. And I think on a test where you're heavily dependent on hand computation and you don't have computer tools to really help you with that, like calculators or Excel or AI, then any place you can reduce the friction of your computation is going to help. And also, I've probably mentioned this 1,000 times in the pod already if you've been a fan for a while or if you've been following for a while. But if you haven't, then allow me to emphasize this again. It's very easy to make computation mistakes, even if you do have the right strategy and the right knowledge on GMAT questions, and there's no partial credit on the exam. I either get it 100% right or 100% wrong. And that can be different from math tests that we've taken in the past. And so the importance of scratch work and of being efficient with your computation without being risky by cutting out too many steps, finding that sweet spot, that balance of the right amount of scratch work is going to be really, really important for 99% of students' success, in my experience. Yes, there's that 1% or maybe even 0.1 or 0.01, if we're being real, percent of people who are just going to get an amazing score no matter what they do. And that's awesome. Good for them. I think we all have our unique gifts that we came out of the womb with, so to speak. But for the vast majority of us, myself very much included, the way you do computation and the way you visualize that during the exam via your scratch work on your scrap paper is going to be a major cornerstone of your success on the quant section. So again, just bringing it back to our lesson, that's why I'm emphasizing the flexibility of these approaches so that over time, as you solve more and more of these questions and you practice, you'll be able to develop a thesis about what is the best way for you personally to approach these kinds of situations, which I think is the ideal way to take the test. Take the test the best way that works for you, that gets you personally the best results. Now, it's important to note that we could have done this a few other ways, kind of digging deeper into this concept of flexibility. We could have isolated y first, and that would have worked just as well. And we also could have isolated x in the other equation, like I was talking about. That would have worked just as well also. So there's no quote unquote right or wrong way when it comes to the order of isolating and substituting. Now, having said that, there are definitely some advisable moves. This is getting beyond just the basics and more into like the strategy of the exam, which I don't want to go too in depth in this series. We'll have plenty more of that to come in the future. But for now, I really want to keep it focused on the basics so you can just get started practicing with good habits. Having said that, I think it's worth mentioning this one strategic tip, which is that you want to solve ideally at the beginning of substitution. You want to isolate the variable that you want to get rid of. That might be worth memorizing. You want to isolate at the beginning of substitution the variable you want to get rid of. For example, if a question asks us to solve for the value of x, and we were given the equations we just used, my first move would be to isolate y. Because substituting for y makes y disappear from the situation, leaving me with an equation that only has x in it that I can then solve for the numerical value of x. Now, it's more of a tip than something essential because, like I just said, you could easily isolate x first, solve for the numerical value of x, and then plug back in for y. That's fine. Or vice versa. But you'll save yourself a couple steps coming back to this efficiency of computation. You'll save yourself a couple steps by isolating the variable that you want to make disappear because that'll leave you only with the variable that you want to solve for. And that's common. That's very common on the GMAT that you'll be given a system of equations and you probably won't be asked to solve for every single individual variable. You'll generally be asked to solve for one of the variables or maybe some combination of variables, which gets way beyond the scope of this lesson, which is why I just wanted to touch on that tip. But that's probably a good habit to develop from the beginning. And that should help with this whole concept of efficient scratch work and quality scratch work that I just was discussing, and that you'll probably hear me discuss a lot because once you've learned all the stuff that you need to know in the quant section, that's the number one battle that folks fight in maxing out their quant score, in my experience. It's a huge, huge deal. So let's model one of these other ways that you could have done this. I don't want to go, I guess, too long doing it like all four ways or every permutation of every way that we could have done it, because that's not important. But I quickly do want to go through one of the alternate methods just to drive this point home. So let's isolate y first this time. We can use the same equation of x plus y equals 10. And if we subtract x from both sides, we would get y equals 10 minus x. Then we can replace y in the other equation with 10 minus x. Recall that the other equation in our system is x minus y equals 6. If we replace y with 10 minus x, we would get x minus 10 minus x equals 6. Now here, we're subtracting 10 and then subtracting negative x. And this gets into an important point about parentheses and PEMDAS, which we discussed a couple lessons back. In general, the habit I'm going to recommend that you use as you develop your substitution skills is when you're substituting in for a variable, always put parentheses around what you're substituting in for. It's basically impossible to go astray or go wrong if you always make the habit of using those parentheses. So for in this case, I would have x minus in parentheses 10 minus x. That's what I would be subbing in for y. So the original equation was x minus y equals 6. And then I'm substituting 10 minus x in for y. And then the way I would write that is x minus open parentheses 10 minus x close parentheses equals 6. And then that way that negative sign in front of the parentheses of the 10 will get distributed to the 10 and the negative x. Again, coming back to the importance of scratch work, visualizing it that way can really help you from falling into the trap of not distributing that negative sign and winding up with x minus x, which is just going to make a nonsense equation of negative 10 equals 6, which is going to be really confusing and potentially panic inducing in the moment during the exam. So, again, just trying to set you up with the crucial good habits that I think are going to monetize long term for you. And basically shave everything else that's more advanced off for a future lesson so that you can get some solidity with the basics here. Again, if you're one of those people who are just building from zero, or maybe even negative math instruction as a kid, like plenty of us got just poor math instruction that set us even further back than no math instruction. And we're having to overcome that. That's totally overcomable. Obviously, it's not ideal. But given that that may be the situation for many of us, let's just confront it, handle it, and move on with handling our business, so to speak. So, again, just to drive this point home and make it as clear as possible, I would recommend making a flashcard out of this and or memorizing that when you're substituting in when you're using the substitution method, however you like to think about that, always put parentheses around the variable and expression that you're substituting in. So whatever expression you're replacing a variable with, put parentheses around that. It's a great habit. You can't go wrong, and it has tons of upside. So once again, we're subtracting the 10 and then subtracting the negative x. Using the parentheses will help you distribute that negative properly. And subtracting a negative is the same as adding a positive. So we'll rewrite the left side as x minus 10 plus x equals 6. Then on the left, we can combine the x's because those are like terms. X plus x is 2x. So now we would have 2x minus 10 on the left equals 6. We can combine the non-variable like terms by adding 10 to both sides, which would give us 2x is equal to 16. Last move is just to divide both sides by 2, which will yield x equals 8. Once we have the numerical value of x, we can plug that back into either original equation to get the numerical value of y. Let's do that real quick in the equation x minus y equals 6. If we replace x with 8, we would have 8 minus y equals 6. And then if we combine the non-variable like terms by subtracting 8 from both sides, we would get negative y equals negative 2. Finally, we can multiply both sides by negative 1, and we would get y equals 2. That should be expected. Recall that when we initially solved for y, we got that y was 2. So all I'm trying to illustrate here is that you can substitute in any order. As long as you obey the rules of algebra, everything should work out great, and you'll get the right solution no matter what happens. Quick final point on this, you don't need to become neurotically obsessed with always making the first move on these equations. In fact, that can be counterproductive. Any move that doesn't violate the rules is better than 0 moves. So if you find yourself getting paralyzed or trying to like plot the perfect path through the problem to get this ideal scratch work I was talking about, that's where you're definitely over the line, and you want to back it off and relax a little bit and just say, look, at the end of the day, I just need to get this problem right. If I end up adding a few extra steps to that, that's not the end of the world. Even though obviously I would prefer to strategize well from the beginning when possible. So that's the right balance point for this. Those are the basics of the substitution method. There's definitely more strategy you can add on to these basics, but let's stay focused just on the essentials for now. Plenty more strategy to come later. In the meantime, now that you hopefully are crystal clear on the basics of substitution, let's make sure you understand the alternatives to substitution, the main one being how we perform the elimination method well on the exam. Now, I've noticed over the many years that I've been doing this that most people are more comfortable with substitution than they are with elimination. And I think this is just because substitution is more commonly taught in schools. But the GMAT, in my personal opinion, favors elimination. You'll more often be rewarded for elimination than substitution. If you're more comfortable with substitution, though, that's totally fine. It's not that you'll be penalized for using substitution. It's just that if you're like, hey, I already know substitution, like forget elimination, I don't need that, I wouldn't recommend thinking about it that way. What we're going to walk through here is going to be super, super valuable. And you'll see this as you get into official problems and official practice exams. Just how valuable this approach is. Even if it's a little bit less familiar, I'd like you to consider overcoming any natural resistance you might have to learning an additional technique. Now, as I mentioned previously, the goal of elimination is the same as substitution. We want to isolate one variable, get the numerical value of that variable, and then be able to solve for the numerical value of the other variables, because that's what we want to do when we're solving system of equations, get the numerical value of all the variables. Elimination accomplishes this same objective in a slightly different way than substitution. Instead of first isolating a variable and then replacing it like we would in substitution, we start by stacking the equations, and then we add or subtract them to eliminate one of the variables through that addition or subtraction. Hence the name elimination rather than substitution. Let's use the same system of equations that we used before just for simplicity and hopefully familiarity at this point. X plus y equals 10, x minus y equals 6. Again, we start by stacking. That means we line up each of the terms vertically. So let's write x plus y equals 10 on top. It doesn't matter which one you put on top, but I'm just going to do that because it's convenient and it's the first one we mentioned. Then right below the first x, we'll write the x from the second equation. So right below x plus y equals 10, we're going to write x minus y equals 6, but we're going to line up all the terms and operations vertically. So x from x plus y goes right over x from x minus y. The plus from x plus y goes right above the minus from x minus y. The y from x plus y goes right above the y from x minus y. The equal sign goes on top of the equal sign, and the 10 from x plus y equals 10 goes right above the 6 from x minus y equals 6. So hopefully you can visualize that stacked vertically. That's the first step of elimination. The second step of elimination is to notice if any of the variables have the same coefficient. If they do, then you'll want to subtract because that's going to eliminate that variable. Okay. For example, in our system, x has a coefficient of 1 in both equations. So if we subtract one equation from the other, x will disappear. Let me illustrate this. If we do x plus y equals 10 minus x minus y equals 6, then the x minus x on the left is 0. The y minus negative y becomes y plus y, so that becomes 2y. And the 10 minus 6 on the other side of the equal sign equals 4. So after we subtract, we would have 2y equals 4 because the x disappears. From there, we divide both sides by 2, and we would get y equals 2. That's the basic two-step process, if you will, of elimination. We stack, and then we look for opportunities to add or subtract to eliminate a variable. Now, the fact that y is 2 hopefully is expected at this point. We already solved for y twice in this system using different ways of substituting. In fact, maybe we even solved for it more than twice. But this is really just an example of when we might want to subtract one equation from the other in order to eliminate one of the variables, and an example of how the basic technique works. Again, that's why this technique is often called elimination. The point is to eliminate one of the variables so that we have an equation we can use to solve for the numerical value of the other variable. One important note here is that it's also a good idea to look for variables that have opposite coefficients. For example, in our system, you'll notice that one equation has plus y and the other equation has minus y. And in that kind of situation where you have these opposite coefficients, one positive, one negative, you should consider adding the equations together because that's going to make that opposite coefficient disappear. So let me demonstrate how that would go. First step is to stack. X plus y equals 10 on top, x minus y equals 6 on bottom. But now, instead of subtracting to eliminate x, we're going to add to eliminate y. If we add, then x plus x gives us 2x, and positive y plus negative y gives us 0, so y is eliminated. Then to the right of the equal sign, we add 10 and 6 to get 16. So we wind up with 2x equals 16. And from there, we just divide both sides by 2 and we get x equals 8. Again, shouldn't be a surprise. We've now solved for x many, many times. But hopefully, it helps you see the different situations where it might be a good idea to add versus subtract. Perhaps obviously in this situation, either way works equally well. But in many situations, one approach will have a clear advantage. So I just want to get your mind thinking about looking for those same or opposite terms to help you figure out if adding or subtracting is the better bet. Now, elimination in that certain situation had several fewer steps than substitution. So why wouldn't we just always use elimination? If like Isaac says, the GMAT favors it, and we're going to trust Isaac's extensive experience here, why not just always eliminate? Seems to be a good way to do things. Well, there are more complicated situations where substitution might be easier. For example, let me give you a slightly more complicated system here. Let's say we have 2x plus 3y equals 30, and then we have 5x plus 11y equals 28. Don't worry too much about the exact terms and numbers here. Just think about this more complex situation where it's not just x plus y and x minus y. Note that if we stacked these, let's just focus on the x term. Nothing's really lining up perfectly. Like you got 2x right above 5x. If we add, that's going to get 7x. But then both y values are positive. We've got positive 3y and positive 11y. So if we add, we're not going to get rid of any variables. It's just going to become more complicated with bigger numbers, and that's probably not going to be super helpful. Similarly, if we just subtract, we're not going to eliminate any variables. Like 2x minus 5x is just going to end up being negative 3x, and 3y minus 11y will end up being negative 8y. We wind up with another equation that's just going to be tough to solve. Now, in this situation, you could still use elimination, but you would have to do a little bit of fancy footwork to make it happen. So, for example, with the top equation, 2x plus 3y equals 30, what you could do is multiply both sides of that equation by 2.5 or 2.5. If you multiply the 2x times 2.5, that becomes 5x. And then that could now match up with the 5x in the second equation, and then you could subtract and get rid of 5x. Definitely not the end of the world to have to multiply both sides of an equation by 2.5, and the technique would definitely still work, but some people find that a little labor intensive up front and also potentially prone to error, because then you're multiplying the 3y times 2.5 and the 30 times 2.5, and some people just don't like to do that. Other people, they're totally fine with it. And again, I'm just going to try to present options to you and help you figure out the best way for you personally to do it. In fact, just kind of extending this for a second, should help out in the future. Another way you could handle this is to find a common multiple of the coefficients if you really wanted to use elimination. For example, with 2x and 5x, we could multiply the first equation by 5 on both sides and get 10x plus 15y equals 150. Then we could multiply the second equation by 2 on both sides, which would also get us 10x, because we're multiplying 5x plus 11y equals 28 by 2 on both sides. So that'd be 10x plus 22y equals 56. And then now we've got 10x lining up in both equations. So then if we subtract, now the x term would disappear and we would be able to solve for y. Again, don't worry about the particulars here. I'm kind of glossing over like the specific numbers. The point is to understand that we would need to multiply both equations by something to get some of the coefficients to line up. And that would still work out. We could still perform the math and get a solution. But that initial aligning of terms through multiplication, again, sometimes this is kind of a lot for people, and they would prefer to just isolate and dive into substitution. I don't think there's a right or wrong. Again, generally, the exam favors elimination if you're excited by the potential efficiency gains of that. And as you go forth and practice, you find that to be a virtuous way of operating for you, then great. I like that way of doing it. I recommend people upskill with elimination because usually they're more comfortable with substitution. But if you're getting great results with substitution, don't change. There's probably plenty of other stuff that you're going to need to change. And ideally, we change as little as possible in terms of what's natural for you in this process and just streamline it. So again, in my opinion, it's important to understand that there's really no right or wrong. But you should be thinking about what you will find best for your personal situation. I encourage you to experiment with that before you get to test day so you have clarity under time pressure. Now, just to wrap that up, if the coefficients of a certain variable do align and it's easy to see, or maybe it's easy to see how they could align with a little bit of adjustment, then elimination will usually be faster and less error prone for most people. But if the terms don't align well, or it's hard to see how they would line up, then just go for substitution. And I think that that's worth memorizing. So I'm just going to repeat that in case it's helpful. If the coefficients of a certain variable line up, or it's easy to see how they could line up with a little bit of math, then elimination will usually be faster and less error prone. If the terms do not align well, or it's hard to see how they would align, then just use substitution. That's how you use the elimination method well on the GMAT. So let's quickly wrap up by talking about the graphical approach. As I stated previously, graphical approach, super rare, super rare on the GMAT. You'd probably have to take the GMAT at least like 5 times to guarantee that you'd even see this once. And even then, it's possible that it wouldn't show up. So it's very rare. Having said that, the concept can come up, especially in the data insights section, because there are a lot of graphs there. So it's worth touching on very briefly, and it'll help drive home a couple of the key underlying concepts that make substitution and elimination work. So think back to our first system that we led off with, x plus y equals 10, x minus y equals 6. We solved this several different ways, yet what was the result each time? Each time we got the same value for x and the same value for y, no matter how we ran the numbers. It always came out with the same result. In fact, systems of equations that are solvable, meaning you're given enough information to solve them, will always result in consistent numerical values for each of the variables. Now, there are only exceptions to this when we get into more complicated situations like variables that involve exponents or absolute values. We'll get to that in the coming lessons. But for now, just to keep it simple, you're always going to get the same values as long as there's no crazy stuff happening behind the scenes. So what does that mean? That means x and y will have the same value in both equations. That might sound a little redundant, but let me just build on that for a moment. What happens if we were to put these equations into a graph? The point at which x and y are equal in both graphs would be called the solution. That's where we have a value for x and a value for y that satisfy and fit with both equations. And if you think about it, the point where these values are equal will always be the point where the graphs of the two equations intersect. And that's true of 3 equations, 4 equations, 5 equations. If you've got a point where all the equations intersect, that value of x and that value of y, or whatever other variables you have going on in there, that's going to be the solution. And the reason that's an important key is just so that if you see 2 graphs intersecting and they ask you for the quote unquote solution to the variables, that solution will be at that point of intersection. So again, probably not going to see that, but just in case, I want you to at least be familiar with the concept so it's not a total shock if it does come up. They can also phrase this in some different ways, such as where each expression would have equal values of x and y. Like they might ask you, like, choose a value for x and a value for y such that each expression above would have equal values for each variable. Like they like, again, taking these simple concepts and making them complicated, but all they're asking you for there is the intersection of the graphs. Okay. I think it's helpful to know that. It could be a little confusing the first time you see it, but yeah, hopefully you'll be able to recognize what's going on there and at least learn from it in your practice problems as you move forward. So that brings us to a good final note. Not all systems of equations are solvable. For example, in general, if you have more variables than equations, it will be hard and sometimes even impossible to solve. I'll repeat that in a moment, but just to be clear, if you have 6 different variables and only 2 equations that relate them, it's very unlikely that you're going to be able to solve for each of the variables. Having said that, there are many tricks of the trade when it comes to this concept, and the GMAT just loves messing around with that rule to create very devious traps. And it's a little bit of a deep topic, so it's something we'll touch on in a different lesson. My goal for this lesson is just to have you understand the basic mechanics of the process so that if you want to go off and start practicing with more advanced questions, you may not know enough to get them all correct yet, but you'll be able to recognize the tricks and the traps that the GMAT likes to try to get us to fall for, because you'll know the basic way that the math operates, and you'll be able to see like, oh, okay, I see why that's wrong. I see what they did there. I'll be on the lookout for that in the future. And that's a lot of what you're going to be developing once you master these basics and start practicing with real GMAT problems, is that pattern recognition. What does the GMAT like to do? And how am I going to counteract that if it shows up on test day? That's a lot of what this study process is aimed at. But in terms of getting yourself a strong foundation for a great GMAT quant score, which is the goal of this program and this course, start to finish, those are the essentials. And you should be well set up to start practicing and learning how the exam likes to make these things more complex on your own. And again, in the future, we will be helping with that, but one step at a time for now. If you'd like some additional practice, as I've been recommending at the end of a lot of these episodes, you can, as of today's technology, use a generative AI tool of your choice, and you can ask it to generate something like a drill set of 5 questions that will help me develop my ability to solve systems of equations on the GMAT. Something like that. Something where you tell it that you want to get better at solving systems of equations and that you're studying for the GMAT. Usually you'll get the best results with a prompt like that or some kind of similar prompt. A lot of you are probably way more advanced with this technology than I am, but for those of you who haven't used it or are worried about using it or who want to get into using it more, this is a nice way you can break the ice with those tools. Now we'll have some drills coming up in the future, and we'll update this episode when those are ready. So please stay tuned. But for now, that's systems of equations. Please reach out, give us feedback if you liked this, didn't like it, felt it was helpful, felt it was unhelpful, ways that you would have changed things, or felt that the information could have been better presented. You definitely can't hurt our feelings. We're here to help. And we want to make sure that if we're going to invest time and energy in creating this material for you, that it is actually bringing you value and it is actually moving the needle for you. With that in mind, my greatest hope is that this material will make your studies as easy and as painless as they can possibly be. If you want more tips and strategies for optimizing your performance on the exam, please head to our website, thegmatstrategy.com, which is linked in the description of this content if you prefer to click rather than type. And check out our free video on how to reach your dream GMAT score in half the normal time. It'll save you a lot of time watching that. In the meantime, this is a regular show, so please subscribe and please stay positive and stay consistent with your studies. Talk to you all soon.